On page 8 of your notes, page 8, we're going to be solving exponential equations. We solved exponential equations in the last chapter, in chapter 7, but when we were solving them, we could, when we had an x in the exponent, we could bring both sides down to the same base. In these examples, we have to use logarithms because you'll see in these examples that you can't bring one of the sides down to the same base as the other side. Like in this first example, we have 2 to the x equals 25. Well, 25 is not any power of 2. We can't bring this down to 2 cubed or 2 to the 4th or 2 to the 5th because 25 just doesn't get reduced that way. So we have to use logarithms in order to solve these exponents. Whenever you solve for an exponent, you have to use logarithms when you have a situation like this. So using exponents or using logarithms, what we say is x is the exponent, right? A log is an exponent. X is the exponent on 2 that gives you 25. And now we're going to take our graphing calculators out because it has a special button where we can do a log base 2. And that special button is under Alpha Window. If you go down to option 5, you have the log base, and you can put a log base anything you want. You can put a log base 2 in there. Log base 2 of 25 is equal to, and then to the nearest tenth they want. So this is 4.6 to the nearest tenth. And that's it. If you don't have a graphing calculator, you can also use just a regular log button. The log base 2 of 25 is the log of 25 divided by the log of 2. It's just a formula that you can use in case you don't have a graphing calculator that has that special button on it. So if we wanted to press the log of 25, close the parentheses, divided by the log of 2, close that parentheses, we get the same answer, 4.6. So either way you want to do it, just depends on if you have a graphing calculator or not. Number 2, we want to isolate the base with its exponent, so we're going to subtract 30 from each side. And we're going to get 5 to the x power is equal to 270. And just like before, x is the exponent on base 5. That's going to give us a 270. So we pull out our calculator, Alpha Window, option 5, and this base is 5, and the argument is 270. So to the nearest tenth, the 7 rounds the 4 up, so this would be 3.5 to the nearest tenth. And that's it. If you wanted to use your other calculator, if you don't have a graphing calculator, this is the log of 270 divided by the log of 5. The log of the argument divided by the log of the base. So in case you have one of these, the log of 270 divided by the log of 5 will give you the exact same answer, 3.5. Just depends on what you have. Number 3, you're going to subtract 4 from each side first, and you get 2 times 2.1 to the x equals 84. Do not ever, ever distribute a coefficient into something that a base that has an exponent. We're not going to call this 4.2 to the x because that's wrong. What we're going to do is we're going to divide both sides by 2 because this is 2 times. So this becomes 2.1 to the x power. 84 over 2, I think, is 42. And now we rewrite it as a log. X is the exponent on 2.1. That's going to yield a 42. So we're going to do log base 2.1, Alpha Window option 5, log base 2.1 of 42 is 5.03. We'll round it to the nearest tenth. This is 5.0. And if you have another calculator, yeah, this one, this is the log of 42 divided by the log of 2.1. So the log of 42 divided by the log of 2.1, which is 5.03, same answer. Number 4, you don't have to isolate the base because it's already isolated for you. The base is already there as e. So in this case, we say 3x is the exponent on base E that gives us 48. And if you want to solve this for x, you're going to divide both sides by, divide both sides by 3. So you get x by itself. The log base E is ln. So we're going to do the ln of 48 divided by 3, and either calculator will do the same thing for you. So the ln of 48, close parentheses, divided by 3 is 1.290, rounded to the nearest tenth is 1.3. In the next example, we want to get E alone. So we're going to first subtract 22. So we have 2 times e to the 2x is equal to, let's see, 378. Divide both sides by 2, and 378 divided by 2 is e to the 2x is equal to 189. Right, we wanted to get rid of that 2 in front of the coefficient. So now we're going to use logarithms because the exponent has an x in it. So we have 2x is the exponent on e. It's going to give us 189. Now we have to divide both sides by 2. So x is equal to the log base e, which is ln, of 189 divided by 2. So either calculator will work. Ln of 189 divided by 2. And that looks like it's 2.6 if you round that to the nearest tenth correctly. The next problem we have, we already have a log base 5 of 219.6. So really this is the easiest problem of all. We're going to just divide both sides by 2. And we're going to do x is equal to the log base 5 of 219.6, and then divide that whole thing by 2. So alpha window, option 5, log base 5 of 219.6. And then I think I'll just hit enter and then divide the whole thing by 2. It looks like 1.67 or 1.7 is x. And if you didn't have a graphing calculator, this would be the log of 219.6 divided by the log of 5. So I would do that in my calculator and then divide that whole thing out by 2 the long way. Either way, you're going to get that same answer. The other problems on these next 2 pages are going to be word problems. So when we do word problems, we have to read these slowly so we can see what we have to replace in the equation that is given. So suppose you receive an inheritance of $5,000 and invested at 5% interest, compounded continuously. We learned that the last chapter. The equation, this is the same thing as P. Last chapter we learned it as P equals, or A, I'm sorry, A equals PE to the RT. That can be used to model this investment. X is the number of years, and C of X, that's just a function like f of X, is the amount of money you have. Well, how much money will you have in 6 years? Okay, X is the number of years, we should circle that. And then this X will contain a 6. So C of 6, right, when you replace that, C of 6 is equal to 5,000 times E to the 0.05, that's the 5% interest, times 6 years. And so we just pull our calculator out, 5,000 second ln of 0.05 times 6. And it looks like we'll have $6,749.29. Make sure you write dollars and cents. $6,749.29. How long will it take for your money to double to the nearest tenth of a year? Well, if we want our money to double, we had $5,000. So to double that, double $5,000, we'll get $10,000 if we want it doubled. So this amount, this amount, $10,000, is equal to the original equation, $5,000, times e to the 0.05 times x, because we want to solve it for years. X is the number of years. And so this time, instead of plugging in x equals a value, we're going to have to solve this for x. So the first thing we're going to do, this is just like the equation before, the first thing we're going to do is divide both sides by 5,000 so we can get e alone. 10,000 divided by 5,000 equals 2. 2 is equal to e to the 0.05 times x. And now we have an equation like we had before, and we can write this as a logarithm because we are trying to solve for this exponent. So we can say 0.05 x is the exponent on base e that's going to give us a 2. And then to solve this for x, all you have to do is divide both sides by 0.05, and x will be the number of years. So we're going to divide both sides by 0.05, and log base e of 2 is just the ln of 2 divided by 0.05. So we do ln of 2 divided by 0.05 in our calculator. And it looks like it's 13.86 years to the nearest tenth of a year. The 6 rounds the 8 up to a 9, so this is 13.9 years. Takes 13.9 years to double your money at 5% interest. Makes sense. The next question, Jordan invests $7,500 at 4.5%, compounded continuously again. So there's that same formula that we're going to be using. Let me get this out here. According to the formula, here's the formula that we learned in the last chapter, A equals PE to the RT. Actually, this is the same formula that we just used on question number 7. A is the amount you'll have after a certain amount of time. P is the principal, that's what you invest initially. R is the rate of interest. And T is time in years. So what we have to set up is the information that we know. Jordan invested $7,500, so that is his principal. His annual rate of interest is 4.5%, so 0.045 is R. And in 10 years, that's the time. Time is 10. And now we can just plug it into this formula. A equals P, 7,500, times E to the 0.045 times 10. And you'll find out how much he has in 10 years. 7,500 times E to the 0.045 times 10. So it looks like you have $11,762.34. Dollars and cents. That's pretty good. In 10 years, from 7,500 to 11,700. How many years? How many years? Well, we're going to try to find, oops, it's not X anymore, it is T, because T is the number of years. We're going to solve for T. How many years does it take to the nearest tenth for the investment to triple? Well, his investment was $7,500. And if it's going to triple, you have to multiply 7,500 times 3, and you should get $22,500 for his investment to triple. That's the amount of money that we want. So A is $22,500. Principal, the amount he invested was $7,500. The interest rate is still 4.5%. And T is, I don't know, that's what we're going to solve for. So we plug in A, 22,500, is equal to P, 7,500, times E to the 0.045 T. That's what we're going to solve for. So here's the equation. Divide both sides by 7,500. 22.5 divided by 7.5 is 3. 3 is equal to e to the 0.045 t. And now we have the base by itself with its exponent. So we can just rewrite this as 0.045 t is the exponent on e that's equal to 3. And we want to get t by itself, so we're going to divide both sides by 0.045. And the log base e is just ln, so the ln of 3 divided by 0.045. You can use either calculator. I think I'll use my old scientific one here. The ln, oops, turn it on. The ln of 3 divided by 0.045. It's going to take 24.4 years for his investment to triple to the nearest tenth, because the hundredth would not round that 4 up to a 5. So the answer is 24.4 years it would take. Number 9, bacteria is being grown for research programs at a college. They have a population modeled by the function. Here's a function. This is like f of x. Instead of f of x, they're calling it b of t. B of t is in thousands of bacteria. So b of t, it's kind of like a y, because remember we said f of x is the same thing as y. We could always replace this with just a y if we wanted to. That's always appropriate. T represents time in hours. Oops, sorry for that bell. T is time in hours. And we're asked to find after how many hours will the bacteria population reach 1 million. Okay, this one is tricky because B of T is in thousands of bacteria and 1 million is 1,000 thousands. This is a little bit trickier than what you'd ever be expected to do on like a test or something, but you should be exposed to this kind of work. So 1 million is equal to 1,000 thousands, and that's what we're going to be replacing B of T with. So B of T is equal to 1.25 times 2 to the power of T. Whoops. Remember, don't ever multiply 1.25 times 2 because this 2 is a base, and you don't multiply the coefficient times the base. B of T is 1,000. 1.25 times 2 to the power of T. Now we're going to have to solve this for T. So you divide both sides by 1.25. 1,000 divided by 1.25 is 800. So 800 is equal to 2 to the power of T. And now that the base is alone with its exponent, we can just use logs. T is the exponent on base 2. It's going to give us an 800. And we can either do our scientific calculator, log of 800 divided by the log of 2 if we don't have our special graphing calculator, or we can just plug in alpha window, option 5, log base 2 of 800. And you get 9.64, and it says how many hours round to the nearest hundredth of an hour. So we look at 2 decimal places, so the 3 keeps the 64 at a 64. So the time is 9.64 hours. One more to go. Population. Population is often modeled by an exponential function. The population of Ghoston, Nevada, must be a ghost town. It's modeled by the function g of t, which is like a y, right? You can call this, it's like f of x, you can call this y equals. And we're given this exponential equation. It's a beautiful thing. T is the number of years since 1980. So we need to know in what year will the population be less than 50 people? Well, if the population is less than 50 people, it must be 49 people because that's the next number less than 50. So if the population, which is g of t, is less than 50, we can say 49. 49 people equals the function 1,824 times 0.896 to the power of t. And when we solve this for t, we'll figure out how many years since 1980 this will be. So let's divide both sides by 1,824. Let's see, 49 over 1824 is 0.0268640,351. Don't round until the very end, is equal to 0.896 to the power of t. Now that we have the base by itself with an exponent, we can use logs. T is the exponent on the base 0.896 that's going to give us a 0.0268640351, and it doesn't take long to write this out. So if you wanted to use your scientific calculator, it's the log of this number divided by the log of this number, or if you have your calculator that does an alpha window, option 5, you can say the base is 0.896 and the argument is, now this has already appeared in my answer, so I can just press second negative because that answer is already this is already stored in that, so I don't have to type the whole thing all over again. So 32.936. 32.936 is how many years since 1980? So in what year is what they're asking for. So you're going to add that to 1980 to get the year that the population will be 49 people. So add that to 1980. And in the year 2012, that was a couple years ago, I guess towards the end of 2012. So in the year 2012, the population will be less than 50 people. And that's the end of this video.